Okay, so this is called parametric equations. Parametric equations. So, we're going to talk about parametric equations. They're actually pretty easy. So, first of all, we're going to define what I mean by a plane curve. So, let f and g be continuous functions. So, listening. Let f and g be continuous functions. So, we have two functions, f and g, different functions, and they're continuous. So, they're functions of t, and they're continuous functions on an interval I. So we have these two functions, and they're continuous functions, meaning they are function, they never break or gap, and they're on a certain interval. So like, for example, from -2 to 3. The set of ordered pairs, x, y, so f of t, g of t, now this would be x comma y, is a plane curve C, where x is f of t, and y is g of t. So really what this means is our x value is going to be a function f, and it's going to be a function of t. Our y value is also going to be a function of t, but it's going to be a function g of t, so a different function of t. So they're both functions of t. So these are parametric equations for curve C, and t is the parameter. So t is going to be considered our parameter. So what we're going to do, guys, is we're going to be plotting points for x and y. It's really easy. It's just one extra step. So we know how to plot x, y points. If you know how to plot x, y points, you know how to graph a parametric equation. Just like you'll see what I mean by parameter. It just means we have an extra variable in there. Instead of just x and y, it's a function f of t and g of t. You'll see what I mean in a second. It will click better. Okay, so these will have direction over time, just meaning we're going to start here and end here. So we're going to draw arrows showing where we started and kind of ended, just showing which direction this has. So maybe write this down on your notes. So we're going to graph the parametric equation on an interval from -2 to 3. So we're going to have our t values are going to be between -2 and 3, where x is t squared minus 4, and y is t divided by 2. So what we're going to do is we're just going to create an xy table, but it's going to be a txy table. So we're going to have kind of 3 things here. We are going to have 3. So we're going to have t, so function over time, and then x, y. So we're just going to be graphing points here. So t is between -2 and 3. So that'd be -2, -1, 0. This is t, because this is our interval here. 1, 2, and 3. So now let's plug in -2 in for x, our x value. So -2 squared, right, is 4 minus 4. No, wait, 4 minus 4, which is 0. Now we plug in -2. Here we get -1. So that's going to be our first point. We're going to plot over 0, down 1. We don't graph t. We just graph x, y. So over 0, down 1, there's our starting point here on this interval. We're just plotting x and y. It's tempting to graph t, but you don't graph t. All right, let's plug in -1. So we plug in -1 squared, minus 4, which is -3, and for x. And then for y, we're going to get we're plugging in -1. So that's -1/2. Is everybody good with that? Okay, so let's plot that point. We're going -3 down 1/2, -1/2. So we're going this way. So we're going to point to arrows, showing which way we're going here. Plugging in 0. So we'll have -4 and then 0. So we're going -4 up 0, connecting these points as we go. Plugging in 1, which would be -3 up 1/2. So it's going like this, so arrows, it's kind of rounded. And then plugging in 2, right? So if you plug in 2 here, that would be 4 minus 4, which is 0, and then 1. So over 0 up 1's a point. So now we're connecting here. So our arrows are pointing. And then plugging in 3. So 3 squared is 9, minus 4 is 5. 3 divided by 2 is 3/2, which is 1.5. Remember that that's approximately 1.5. So we're going over 5 up 1.5. So there's our arrows. Now, really, this is going to continue, but we're only graphing it on a certain interval. So if I was going to graph this, if it didn't say over an interval, basically it would continue like this. We just plotted points. Yeah, we only plot x, y points. And then we only graphed it over that interval. I was just showing you that it could continue. Yes? Because it's got to have direction. So wasn't that how what happened? So basically, if we had a particle sitting here and it moved, it would move like this and end up here. Isn't that the order it went on time? Does that make sense? It went in this order. So we're just showing like the direction it went. Good question. Okay, let's do another one. Okay, graph a parametric equation on an interval between -1 and 3/2. So we're going to have a t, x, y. So -1, 0, 1, and then isn't 3/2 1.5? So that's good enough. Let's graph those. So we can graph as many points as we want. You guys get what I'm saying, right? We could plug in anything. Okay, let's plug in, so our x, oh, what the heck? I didn't even write it down. Sorry, guys. Where x is 4t squared minus 4 and x equals t. Y equals t is what I meant to say. Struggling. So we would plug in -1 right here. So -1 squared is 1. 4 minus 4 is 0. Correct, everybody? And then if we plug in -1 here, we get -1. So over 0, down 1. There's our first point on our graph. Once again, we're just plotting our xy points. Plug in 0, we get -4. Plug in 0, we get 0. So -4 of 0. Isn't it connecting like this? Arrow, okay, and then plug in 1, so that'd be 4 minus 4, which is 0. Plug in 1, we get 1. So over 0 up 1, so it's coming around, circling this way. So arrow's pointing the direction it's going. Plugging in 1.5, so let's just quickly put it in our calculator, or we could think about it, but let's just make our life easier. 5 is this, and then plug in, 1.5, and that's 1.5. So we're going over 5 up 1.5. Doesn't that look exactly like the other one we just graphed? But didn't that happen much quicker? I'll show you. So what I mean by that is, these graphs look the same. They were different parametric equations, but their graphs were the same. Now this red thing happened between -2 and 3. Didn't that take us plugging in a bunch of t's to get there? Many more t's, then didn't this happen much quicker? Wasn't there only 4 points versus many points? Yeah, so we got to this point over a smaller interval of time. So didn't that happen quicker? So that's just what it's pointing out here. Is that sometimes you can get the same graph, but over a quicker interval, depending on what equations you're looking at. Does that make sense somewhat? Okay. Okay, awesome. So now, here's the thing, guys. It's kind of a pain to have to graph t, x, and y. So we can make our lives easier by, it's called removing the parameter. So instead of having functions of t, let's just have our function in terms of x and y so that we don't have to graph t, x, and y. So we don't have to plot t, x, and y. That's called removing the parameter. Now, if you remove the parameter, then you're just graphing x and y. You're just finding points for x and y. That makes it easier. So for example, everybody, look at this problem. Write it down. And then make sure you write in your notes that what we're doing here is we're removing the parameter. Meaning we don't want functions of t. We want functions in terms of x, y. So now think about it. We can do this 2 different ways. We can graph this 2 different ways. What I want you to notice is over here we could simply solve for t and get our function in terms of t instead of y. So have t equals something. Does that make sense? So to do that we would divide by 2, divide by 2. So now we have t is equal to y divided by 2. So now what we can do is take that and replace t in this function with y over 2. So now we have x is equal to y over 2, replacing t squared, minus 4. And now do you see how we have this new equation that's just in terms of x and y? Isn't it easier to find x and y points for just those, just that? Does that make sense, everybody? Yes. And you could do it the other way, and I always like to do it the other way because I like my function to be in the form y equals. So yeah, with this one, we're not going to graph it, so it didn't really matter. But in all the others, I'm always like, I like y equals something, so I always go the other way. So here we go. Let's just simplify it. So x is equal to y squared over 4 minus 4, correct? Does everybody see what I'm doing here? Okay, so then we would rewrite that just pretty style. X is equal to 1/4 y squared minus 4. So because that's in terms of x and y, it's x equals, it's actually going to be a sideways parabola, but we're not graphing it. So it's just showing that we removed the parameter. So fun fact for you, when you remove the parameter, we could, if we graphed this, it's going to look the exact same as if we graphed that using t. Does that make sense? It'd be the exact same graph. It'll look the exact same. Okay, so let's do this one. So write this down. So it says graph the parametric equation. So we're going to eliminate the parameter and then graph it. So eliminate the parameter, then sketch the graph. So once again, I'm opting for y equals to stay y equals so that I can graph it without much thought put into it. So I'm going to get rid of, removing the parameter means get rid of this variable that's in t and get rid of it. So let's do algebra to get t equals instead of x equals. So what would we do? There's a couple different ways. I like that. Multiply both sides by root t. So over here we have root t x equals 1. Next step, divide by x. Because remember, our goal is to get t alone. So we have root t equals 1 over x. To get t alone, square both sides. So we have t is equal to 1 squared over x squared. So we'll write t is equal to 1 over x squared. Now notice, now we can take and replace t with 1 over x squared. So now we're going to have a function y equals and a function of x, which will be nice. So y is equal to, we have 2 times, instead of t, we have 1 over x squared and then squared. Let's simplify it before we graph it. So we have y is equal to 2 times, technically we have to square both of those, so 1 squared over x to the raise a power to a power and you multiply. So we're dealing with graphing 2 over, that's kind of an ugly shift, 2 over x to the 4th. Yeah, we can multiply fractions straight across. So now graphing that, you're going to have to remember how graphing of rationals works. So guys, if we graph this, it's the same thing as if we were to graph this with a t. Okay, so what I want us to do is graph this. So let's think about where our vertical asymptote is. Isn't that when we divide by 0? Remember back, it's been a long time. So we can't divide by 0. So it doesn't that happen. We have 2 over x, right? X to the 4th. So x cannot be 0. So that's where our vertical asymptote comes from. So that's what you would draw on first when graphing it. Because you can't divide by 0, that's where vertical asymptotes come from. Remember back to graphing these, it's been like a couple months. Then to find your horizontal asymptote, remember you take the top function divided by the bottom function. How many times does 2 divide into x to the 4th? 0 times, right? So 0, our horizontal asymptote is at 0. We'll review all this in just a second because a lot of you forgot. Well, I have a whole slide reviewing how to talking about this. Good, yeah. So now let's think about it. Okay, now let's think about what an asymptote means. Okay, so this might help. If we plug in positive infinity, 2 divided by positive infinity is pretty much 0, correct? Or let's think of something like a little bit more like easy to visualize. 900. 2 divided by 900 is pretty much 0. So do you see how we're going to get really close to 0 but never actually be 0? Does that make sense? That's the definition of an asymptote. So now let's plot some points. Let's plug in 1. 2 divided by 1 is, so I'm just plotting points. So I'm going to plug in 1. So isn't that 2, guys? Over 1 up 2. Let's plug in maybe 2. So 2 divided by 2 to the 4th power, that's getting smaller, correct? 2 to the 4th. So that would be 2 over 2 to the 4th, which is 2 over 16, which is an 8. So we're going over 2 up an 8. So we know though it's going to approach this asymptote. So it's going to come down like this. Now let's plug in a small value, meaning a decimal right here. Let's plug in maybe a half. So let's plug in a half and see what happens. 2 divided by 1/2 to the 4th power. It's 32. Does everybody get that? That's right. But does everybody understand how we got 32? Yeah. So awesome. So over a half of 32, which makes sense because we know that it's going to approach this asymptote. We calculated 1/2. We just plug it into the function. So that's 2 over 1 divided by 2 to the 4th is 16, right? Dividing fractions is easy as pie. Put the second in, multiply. Okay, so now let's plug in -1. -1 to the 4th is going to be +1, right? So it's going to reflect over this way. It's going to look the same, right? Because any of these negative points are going to become positive. So it's going to look the same here. So, and we've graphed it. No, because think about it, we can never be down here, right? We can never be negative, because won't this always be positive when you raise it to the 4th power? Good questions. Right. Cool, that's it. Like, it was just, so basically what it was is we removed the parameter to make our graphing a little easier. Does that make sense? Instead of having to graph t, x, y? Yeah. Okay. All right, so I just want to remind you of how asymptotes work, because you're going to be dealing with that. So everybody look at this. If we were dividing this, and I'm talking horizontal asymptotes, because remember, vertical asymptotes are just when the bottom equals 0, correct? Those are easy. So it's the horizontal asymptote that is a hard thing. And this is what you're going to see in calculus. You're going to be doing limits, and you have to be able to visualize what an asymptote means and why it works. So everybody listen. So an asymptote means as x gets larger and larger, where's your function approaching? Like, where's it growing to? So everybody, if we have 3x squared plus 9 divided by 2x squared minus 3, remember the rule was, if you have the same exponent, don't they divide evenly? Yeah. So our asymptote would be at y is equal to 3/2. Well, let's think of why that works. Just a reminder of why that works. What? That doesn't matter, right? If you remember back to graphing rational functions, and we'll talk about y in about 30 seconds, if you have the same exponents, isn't it just the leading coefficients that it approaches? It is. That was the rule. But think about why that works, guys. If we plug in as x approaches positive infinity, meaning as we get really, really large, is this, we plug in infinity here, is this plus 9 going to affect anything? Not really, right? But isn't this 3 going to matter? Yeah, because 3 times like something really large squared. Now, but then think about it. You'll be dividing by that same really large number, correct? We're plugging in the same number. Does everybody see? So do you see how just these leading coefficients are all that matters? Because your large number part divides out. Does that make sense, everybody? The 9 and 3 won't affect because you're getting so large that it's going to approach 3/2. Does everybody see what I'm saying? Let's even test it out. For example, 3/2 is 1.5, right? Okay, I want you to type into your calculator for me right now. 3 times 1,000 squared plus 9. Divided by 2 times 1,000 squared minus 3. Unless your calculator says error because it's too large, but I think it should work. Like we're typing in a really large number for x, and let's see if it is really close to 1.5. Yeah, so do you see how it's approaching 1.5 as we get larger and larger? Does that make sense though, why that works? Because these are barely affecting it. Does that make sense? You're going to have to know that for calculus. If it doesn't make sense, tell me so I can better explain. So we would have it on a graph. So as x approaches positive infinity, our function approaches 3/2. So that means we would at 1.5 have a horizontal asymptote. Okay, let's do this one. As x is approaching, so let's think about this one. 3 divided by x. What's it going to be? Anybody? Like, what's our horizontal asymptote going to be? 0. Well, why does that work? Because let's type in 3 divided by 1,000. Pretty much 0, guys. Type it in. 3 divided by 1,000. See how it's pretty much 0. Okay, so as x is approaching positive infinity, our function's approaching 0. So this one would be 3 doesn't divide by x at all, 0 times. So this would be where we had our horizontal asymptote of 0. So then this is where we got oblique asymptotes, when the top was smaller than the bottom. Does that make sense? Because it does divide, but it's not evenly, and then we're not going to get into that, though. We're not going to get into that, but just a reminder. A slanted asymptote. Instead of horizontal, it becomes slanted. It becomes linear. As well, x, when you divide x, you get what I'm saying? No, wait. Did I have that backwards? No, wait, x squared divided by x cubed 0 times, doesn't it? So it should have been this. My fault. It just should have been the other way. This should have been a 3, this should have been a 2, right? Because then it does divide, but just not evenly. My fault. I just wrote that wrong backwards in my head. Asymptote? Yeah, technically. Okay, so here's another example. We're actually almost done with the lesson. So it says grafted parametric equation. This one always throws people off. And it would be really nightmarish if we don't eliminate the parameter. So it says grafted parametric equation. So when you're given a parametric equation, it just means you're given a function x, a function for x, and a function for y. So, and notice we have x is equal to 2 cosine theta, y is equal to 2 sine theta. So our parameter is theta. That means we have functions of theta. Just like when we had functions of t was the parameter. Now we could graph those by doing t, x, y, but that's going to be a nightmare to graph. I don't want to graph that. You don't want to graph that. So you would say it's going to be better if I eliminate the parameter. Does everybody understand? So let's get it. So we have x is equal to 2 cosine of theta, and we have y is equal to 2 sine theta. And let's get rid of theta. Let's get, no, let's not. What we're going to do is we're going to divide both sides by 2 here. So we have x over 2 is equal to cosine of theta. Now, if we were to undo cosine, we're going to be talking cosine inverse, which is still nightmarish. So we don't want to do that. I'm going to explain in a minute what we're going to do with sine and cosine. Now, over here, we would divide both sides by 2. So we have y over 2 equals sine of theta. Now, instead of trying to solve for theta, let's think of an identity that allows us to relate these and write them out nice and pretty style. Anyone think of an identity for sine and cosine that comes out pretty? Sine. Good, Dylan. So sine squared theta plus cosine. So you're going to find with sine and cosine, you're going to find something that relates them and use that. So sine squared theta plus cosine squared theta equals 1. So let's plug in everything that we know here. So we're eliminating the parameter. So what we're going to do is instead of sine squared, we're going to put in what sine is equal to, right? Do you see what I'm saying? Because this is really just sine of theta squared, right? Yep, so this is going to be, sine is y halves. So we have y halves. I just thought you said 1/2. So we have y half squared plus, and then this cosine squared, so that'll be x over 2 squared equals 1. And now we can keep simplifying this. But isn't that prettier to graph, though, than graphing sine and cosine? Yeah. So now think about it. That would be y squared over 4 plus x squared over 4 equals 1. And I like to say, I don't want to graph, I just want to graph, this is a circle, guys. If you remember back to secondary 2, that's what a circle looks like. That's the equation of a circle. However, I like to graph circles when there's no fractions, so let's get rid of 4. So isn't this the same thing since they're both over 4? That's the same thing as this. Y squared plus x squared over 4 equals 1. Can we put them over the same fraction? Good. Multiply both sides by 4. So now we're dealing with x squared plus y squared equals 4. Now just a quick reminder, it's been a long time since we've dealt with circles, but circles have this form, x minus h squared plus y minus k squared equals the radius squared. where our center of our circle will be at h comma k, so the shift. Yeah. So if it's in parentheses, we always go opposite, just like with other functions. Good question. So then our radius would be obviously come from there. Yep, so our center here is at 0, 0, because look, no shift left and right, no shift up and down. And so it's at 0, 0, and our radius squared equals 4, so that's r squared, so our radius is 2. So now we'll go up to our picture, and graphing that circle is much easier than graphing sine and cosine on that interval. Okay. So we're going over 0, up 0, and then over 2, up 2, over 2, down 2. Now, however, if we would have graphed this and this on that interval, it would have looked the same. But to me, it's easier to eliminate the parameter, still with graphing an XY type problem. Kind of weird. I agree. No, you don't. It's not that bad. I know, but it's not that bad, right? Okay, questions on that? Okay, this is my last example. Then the rest of the time is all you. So it says, write the parametric equation. So you're going to be given y equals 1 minus x squared. Now part A, like for example, let's write a parametric equation. Now remember, what does a parametric equation mean? It means you have an x, y, and they're both functions of t, for example. So it says, given that x equals t, what are the x, y points, basically? So if x equals t, then that's our x function, right? Now we need to find our y function. So if x equals t, then won't that be 1 minus t squared, guys?
Yeah.
So then that's our answer. Well, we were given that. We're given this, we're given this. So we know that x equals t is the x value, because remember, x, y points are parametric equations where x is g of t and y is f of t. So do you see how we have a function of t, a function of t? Different functions, so this is our answer. That's the parametric equation. So, yeah, this is part B. We're just doing a whole different problem here. So understand, guys, if we were to graph this, it's the same thing as graphing this. Well, that's going to be easier to graph, isn't it? So just keeping in mind what a parametric equation means and what you can do. Any questions?
I'm actually confused.
I think x must equal to over.
No, that's just I was underlining it saying that's my answer for x. We were given that. You're given this, guys. You're given x equals t. So it says find the parametric equation. So that just means you have to have two equations in terms of t. So we were already given x was t. So we're done with that, right? This is a whole different problem.
No.
So if we know x is t, we plug that in there so that we can figure out y in terms of t. Okay. Let's try another one. All right, now let's pretend like we're given y equals 1 minus x squared, and they want us to instead, because that's not parametric, right? Y equals the function is not parametric. So now they're saying write a parametric function if x equals t minus 1. Yes.
When would you ever want
It's you use it in physics because then it gives it direction. You know what I mean? But so I'm teaching you the math so that you can go to physics and apply the math. Yeah, exactly. Really smart people go into math and brilliant people go into physics because it's all applied math. Okay, so here we go. Part B, it says now instead, given this equation, write a parametric equation in terms of t. So we know that x is t minus 1, so that's going to be our x value for the parametric equation. That's given. Now we need to find our y value. Replace that with that, right? So you guys get what I'm doing? Just putting it instead of a function of x, now a function of t. You guys get that? Oh, like I was just rewriting what was already there.
Yeah.
Got it. Okay, so now we would have, let's do the algebra correctly. 1 minus parentheses, t minus 1 squared. Now I'm not going to break the forbidden rule because I'm not at that point anymore. So I'm going to subtract all that stuff, so I need parentheses. If I double distribute that out, FOIL it, double distribute's better, t squared minus 2t plus 1. Isn't that true? Now we would distribute the negative, so that would be 1 minus t squared plus 2t minus 1. So our y value is actually going to turn out to be 1 minus 1 is gone, so we have negative t squared plus 2t. So this is a parametric equation. This is not. But we were able to create a parametric equation. That just means write x and y in terms of t. That's all you got to do. It was negative t squared, right? Plus 2t. And I just rewrote it in standard. I just have it in standard form. So one more thing, just a reminder. If I was to graph this, it would look the same as graphing this. Not that we are graphing it, but that's... Does everybody understand?
Yeah.
Whew. Hey, there's the problems. Not a whole lot. Not a whole lot.